Alright, so let us recall what exactly we had done till the previous class. The idea was that given a matrix A which was M cross n, there was a notion of elementary matrices and what were they? They are of three types: ek of C, C is not 0. So, I am multiplying the kth row by C of identity. Then I had Eij of C, that what you are doing here is you are replacing the ith row by ith row plus C times the jth row, all right. And then there was Eij itself, which was the interchange of ith and jth rows. So, these are the three elementary matrices that we had, and they are invertible. So, they are invertible as well. We also had this definition where we said that definition was that there are two matrices, A is M cross n, B is M cross n. So, they are row equivalent, if A is equal to P times B for some invertible matrix P, all right, fine. So, the idea was that row equivalence was an important role for us, and we got it through the invertible matrix P. What turned out was that elementary matrices are invertible. So, when we try to solve the system, we could write the augmented matrix A B. So, we are solving the system A x is equal to B, then you have the corresponding augmented matrix. We went to RREF and got the matrix C D, and going to this was basically multiplying by a sequence of elementary matrices. All right. And if I take a finite sequence of elementary matrices, each of them is invertible. So, the product is invertible. So, basically they gave me an invertible matrix and we wrote it as P itself. So, we wrote it as P. We wrote the product as P or E or F, whatever it is, invertible matrices. This is what we did, fine. The main theorem that I did not prove was, the RREF of a matrix is unique. So, I did not prove it because it requires going out of the system and then coming back, fine. So, therefore, we just assumed it. Based on that, we could do a lot of calculations. We could prove the first thing that, so one of the things that we could prove was, or propositions or results, whatever it is, was that if I take A is M cross n, its RREF is F, take B which has columns, first column till S columns, all right, and S is less than or equal to n, then RREF of B was nothing but the first S columns of F itself. We could do this, all right, fine. And from there, we could also do this, that if, so we looked at the system A and identity. Here we took A to be n cross n, looked at its RREF, I got it as R and E, fine. So, if I relate the two, so RREF basically means multiplying by a matrix here something. So, I multiply by P, which is invertible. Then what we see here is that two matrices are equal if they have the same components. So, that implies that P times A was R and P was E itself, and therefore, here I could say that E times A is R, fine. Now, E is product of elementary matrices and therefore, it is invertible, and this implied that if R is identity, then A is invertible. Else we could not say what will happen to the next part, all right. So, if R was not identity, it means that A is not invertible. So, this is what we said, that if R is IN, then A is invertible. If R is not IN, then A is not invertible. All right. What you have to keep in mind here is that to show that A is invertible, we did not prove that AE is equal to EA is equal to identity. Did not do this, did not prove it. What we did instead was, we just showed E times A was identity, and we knew and we know E is invertible, and therefore, its so this will imply that its inverse is unique, inverse of E is unique, and therefore, this gave me that E inverse is A, and this implied that A is invertible, all right. So, in place of showing that A is invertible directly, that is to show that this happens, we went roundabout and then got the result. Is that okay? Now, as a corollary of these ideas, I will just state some theorems here. So, corollaries. First corollary is that if A is invertible, let A be invertible. Suppose I have a matrix A, B, which looks like A and C here, all right. Then what can I say about B? Then RREF of B is IN and 0, fine. 2. If B is A times C, then RREF of B is IN and whatever it is. So, since I am multiplying by A inverse to get identity here, it will be A inverse of C, fine. So, you have to keep track of this, so that those ideas can be used at a later stage, fine. I will not prove it, we will just take it as it is, fine. Now, what we had learnt was that when we apply the Gauss elimination method, we got different matrices. The obtained matrix, the final matrix, not to be same for all of us, all right. So, this helped. So, this was a problem for us. So, from there we went to the Gauss-Jordan method or the RREF, which gave us uniqueness, fine. But recall that the number of pivots remain the same. fine. So, now I can do one thing, that this is this matrix RREF is unique for all of us. We can use the number of pivots there to define what is called the rank of a matrix. So, we define definition A is m cross n, fine. The row rank of A is defined to be the number of pivots. So, it is number of pivots in RREF of A, fine. So, to define the row rank of a matrix, I was forced to go to RREF because we needed somehow to say that number of pivots are going to be the same. That I could not guarantee when I am looking at the Gauss elimination method, but using the Gauss-Jordan method, where I know that the matrix is unique for all of us, it is the same for all of us, we could say that the number of pivots there will be the same, and therefore, the number of pivots is same. So, I can talk of that as an object, that is a number, and therefore, I could define row rank of a matrix, fine. But if you want to find the row rank of a matrix, you just have to do the Gauss elimination method, because as we said, the number of pivots do not change when I go from Gauss elimination to Gauss-Jordan, fine. Now, at this stage, I am using the word row rank basically because my calculations are based on only rows. I am multiplying the matrix A on the left by elementary matrices, fine. Question arises that if I had started with applying some column transformation, applying elementary matrices on the right, will this number remain the same, fine. So, I do not know at this stage whether they are same or not, but what I can say is that I am also going to get certain number of pivots, and I can define what is called the column rank of A because I am multiplying matrices on the right, fine. It turns out, we will prove it when we go to vector spaces and so on, prove that row rank is same as the column rank, fine. So, for the time being, I will not use the word row rank, even though I am defining row rank, I will just use the word rank of a matrix. A rank of A is nothing but number of pivots or number of non-zero rows in RREF of A. So, you have to compute RREF, or you have to get the REF, the reduced echelon form, all right, the row echelon form to get your rank, fine. So, let us take up some example to understand it. So, example. So, I have this matrix A which is 1, 2, 2, 4, fine. So, if I look at the RREF of A, it will be, I can just use this to make this one 0. So, it is 1, 2, 0, 0, and this implies rank of A is 1, fine. 2, take A equal to 1, 2, 3, 2, 4, 6, again the RREF of A is 1, 2, 3, 0, 0, 0, and therefore, rank of A is 1 itself. If I take A as 1, 0, 0, 0, 1, 0, 2, 2, 0, fine, then the RREF of A is 1, 0, 0, 0, 1, 0, 0, 0, 0, implies rank of A is 2. In general, you can see that rank of a 0 matrix is 0, rank of identity matrix of size n is n, fine. Another thing that I would like you to understand is that suppose I take, so I had my A as 1, 2, 2, 4, fine. I take B as, all right, so let us take B as say -2, 1, fine, and say -2, 1. Suppose I take this, let us multiply what is A times B. So, A times B is 1, 2, 2, 4 times -2, -2, 1 and 1. So, this turns out to be this into this, multiply this by minus 2, 1 times minus 2 and 2 times this will give you 0 0. Similarly, this into this will give you 2 times this is minus 4 minus 4. So, 0 0 implies rank of AB is 0. What about BA? If I look at BA, minus 2, 1 1 times 1 2 2 4. This is equal to, multiply this by minus 2, multiply this by minus 2. So, you are multiplying this by minus 2 means you are looking at minus 2 minus 4 and then it is minus 8. So, minus 6 minus 12 and this turns out to be 1 plus 2 is 3 and 6, fine. So, if you look at this again I can multiply this by 2 and add, I will get 0. So, this will imply that rank of this matrix BA is 1. So, here I see that rank of AB need not be equal to the rank of BA, fine. So, these are important ideas that you need to understand, that I can have issues with AB and BA, commutativity does not hold, not only that rank also may not be the same, fine. So, let us now build up some theory again. I will just write the statements which you can see easily, fine. So, 1, if A and B are row equivalent, then rank of A is same as rank of B. 2, if A is m cross n, then number of pivots has to be less than or equal to m, because in each row I am supposed to have at most one pivot. Also, number of pivots will be less than or equal to n, number of columns, as every column can have at most one pivot. So, here it was every row can have at most one pivot. Here it is number of columns, again here every column can have at most one pivot, all right. So, therefore, what we see is that rank of A, which is m cross n, is less than or equal to minimum of m and n, fine. 3, B is equal to, if B is equal to A 0 0 0, then rank of B is same as rank of A, all right. Or in general, if I want to write B is equal to say AC 0 0, then rank of B is equal to rank of AC. So, whatever you want to say, you can build upon those ideas. 4. So, this part, the first part says that they are row equivalent. Row equivalent means I am multiplying by invertible matrices. So, when I am multiplying by invertible matrices, the rank does not change. So, what we are saying is indirectly, which is same as 1 equivalent to 1, that if A is equal to P times B and P is invertible, then rank of A is same as rank of B, fine. We already saw in the previous example, let us look at, go back 72 here, that look at A and B, the rank of these two matrices is 1, they are not invertible. So, A and B are not invertible. in this example. All right. When they are not invertible, the rank can either remain the same or they can also reduce. Fine. So, both the things are possible. So, if B is equal to C times A, then rank of B will be equal to rank of less than equal to rank of A. I am multiplying C on the left. Is that okay? That is important. So, depending on what it is, things can change. I have already given you some examples. All right. One more thing that I would like you to say is that, so this part is there, this is there. Now, one very important theorem now, and I would like to prove it, but the second part becomes a bit difficult in the sense that you have not seen it, but I would like you to understand it. It may take time. So, suppose that I have matrix A, which is M cross N, everything is real number or complex numbers, and rank of A is equal to R. Fine. This implies there exist invertible matrices P and Q such that PAQ is IR 0 0 0. All right. So, the important thing is, till now we have been doing only left multiplication. All right. Here we are multiplying left as well as right. So, there is right multiplication also. Right multiplication by invertible matrix. All right. So, this idea cannot be used, since I am multiplying on the right, this cannot be used for system of equations. So, this cannot be used directly for solving system of linear equations or whatever algorithm that you are doing, that Gauss-Jordan algorithm and so on, we cannot use these ideas, fine. But this rank idea can be used and done something else when I am not solving a system of equation, or when I am just looking at the matrix A, the row space of that, column space, all those things I have not yet defined, but looking at A itself and trying to understand the matrix A, fine. But we are doing everything with respect to rank. So, let me first take an example and then I will give a proof of this example. Suppose my matrix A looks like 1 2 3 4, 2 4 5 1, 1 2 4 7. Suppose I have this matrix with me, fine. I want to compute the RREF of this matrix. So, if I want to apply the, so let us do some things here. So, I just leave it as is 1 2 3 4, multiply this by 2 and subtract, you get 0 here, 0 here, 5 minus 6 is minus 1, 1 minus 4 is, all right. So, 1 minus 8 is minus 7, this is 0 0, 4 minus 3 is 1 and 7 minus 4 is 3. I have this. At the next stage, I can take it as 1 2 3 4, there is this pivot that I have, these are the pivot, 0 0 1 7, this is my pivot, 0 0, I can just 0 here and just adding it, so minus 4. At the next stage, I have 1 0 0, 1 is a pivot, 2 0 0, 3 1 0, 4 7 1, all right. So, I have applied the Gauss elimination method and also multiplied by 1 upon minus 4 to get it 1. Fine. Now, to proceed further, I have to use this one to make these two entries 0, use this one to make this entry 0. All right. So, we can do that at one go. I will not write the matrix here. So, what we have here is 0 0 0 1, 0 0 1 0, 1 2 0 0. I get this. Fine. So, this was all applying to till this stage, only applied row multiplication. Or row multiplication means left multiplication on the left. Fine. Now, what I would like to recall that I had said that if the number of pivots is r, the RREF will have I sub r sitting inside it. Since the rank is r, so the number of pivots is r, and therefore, we will have IR sitting there. All right. Here in this case, it turns out that the rank of A is 3. This is what you see, there are 3 pivots, 3 pivots, and therefore, I have got I 1 0 0, 0 1 0 and 0 0 1 sitting here. Fine. So, therefore, what we can do is that we can multiply something on the right here. So, for example, in this example, let us interchange. So, I keep the first column as it is, I do not do anything. I want to make the third column as my second column. All right. So, I want my third column to be my second column. So, it is 0 times this plus 0 times this plus 1 times the third column will give me this part. Fine. I want to make this as my third 0 0 0 1 and I keep this here. So, if I multiply this matrix here on the right side, fine, then what I will get here is, just have a look at it, 1 times this will give me 1 0 0, 0 0 1 will give me 0 0 1, which is 0 1 0, the third one will give me 0 0 0 1, it will give me 0 0 1, and this one will shift to here 0. Fine. Now, again on this I can look at this column minus this. All right. So, fourth column, so I am not doing anything to the first column, I am not doing anything to the second column, not doing anything to the third column, and fourth column is being replaced by fourth column and minus 2 times the first column, minus 2 times the first column. All right. So, look at this, if I multiply this on the right again, this matrix would turn out to be IR 0. Fine. So, it is I 3 and 0 here. Fine. So, what I am trying to say is that this is the way I am going to get the matrix Q. I am going to get some things here. Fine. So, let me go back and give the proof of that. So, proof. I have A was m cross n, rank of A is R. So, this implies there exists an invertible matrix P such that P times A is going to give me some B here, 0 here. Fine. Important, rank of A is same as rank of B, which is equal to R, implies I sub R is a submatrix of B. So, this implies we can interchange columns of B, all right, or which is same thing as saying equivalently multiply by a permutation matrix, on the right of P A to get P A Q 1 will be equal to, now I R will be there, there will be some B1 here, 0 here, 0 here, fine. Now, all right, once I have got this, then I can make all these entries 0 using this IR. So, look at the first row of B1, I can make this 0 using the first column of IR, which was 1 0 0 0. I can use this to make every entry here to be 0, fine, as I did in the previous example, all right. So, again, but I have to, since I am doing column transformation, I am using the first column to make this entry 0, I am going to multiply on the right. So, multiply on the right. Is that okay? So, therefore, what we are saying is that similarly, to make the second row of B1 to be 0, I have to use the second row of IR, which will be 0 1 0 0 0, fine. So, this way I can make all the entries of B1 to be 0, or I can just multiply by some matrix and then get them to be 0. So, what we are saying is that now we can again multiply by an invertible matrix, matrix Q2, so that PA Q1 Q2 is IR 0 0 0, fine. And this Q1 was the matrix Q that we looked at, because Q1 is a permutation matrix. Permutation matrices are invertible, not only that, they are inverse the transpose itself, and Q2 is invertible. So, Q1 Q2 is invertible. So, therefore, we have got here PAQ is equal to IR 0 0 0, all right. I will take 5 more minutes to just explain you what is the implication of this. So, now I can write, so since once I have got this, so as a corollary of this, so I wrote PAQ as IR 0 0 0, where R was nothing but rank of A, fine. So, what we would like to do is, so from here what I can get here is that A is nothing but P inverse IR 0 0 0 Q inverse. Now, I want to decompose. So, decompose P inverse and Q inverse, so that matrix multiplication makes sense, all right. So, let us see here, I have IR here, 0 here, 0 here, 0 here. This matrix was M cross N, fine. So, there are R rows here. So, there are M minus R rows here, there are R columns here, there are N minus R columns here, fine. What I know is that this Q is N cross N matrix, so that the matrix multiplication makes sense. P is M cross N. So, let us decompose it accordingly. So, I can write Q inverse. If you look at Q is N cross N, there are N columns here. So, I would like to break it accordingly. So, I want to write it as, say, C1 here, C2 here. What is the size of C1? I want to multiply this into this. So, there has to be R rows here and there has to be N minus R rows here, fine. Similarly, here I can break P inverse as, say, all right. So, I think B1 has already been used, or in your scholars B1, B2. Now, here this is R, this is M minus R. So, this has to be R, this has to be M minus R columns, all right. So, R columns here and M minus R columns here, fine. Once I have done that, so this is the writing, this I wrote it as P inverse is this and this is Q inverse for me. So, A remains as it is. So, this is same as, let us multiply it. You get here this into this is B1, fine. this into this is 0 times C1 C2, which is equal to B1 C1. Fine. So, now let us look at this. So, B1 is of size m cross r, C1 is of size r cross n. So, therefore, we have got A as B1 C1, where rank of B1 is equal to rank of C1 is equal to r, and this is called the rank factorization of A, all right, because the rank of A was r, and we have written A as product of two matrices each of rank r. So, wrote A as product of two matrices of rank r, which was the rank of A itself. Is that okay? So, this is called the rank factorization. As I said, this is called the rank factorization, and this was one of the things that we wanted to do as our aim. Our aim was to look at LU decomposition that we had done earlier. This is the rank factorization, which was the second step, and after this whatever factorization we are going to look at is going to be quite complicated, and therefore, we will have to understand what are called vector spaces, inner product space, linear transformation, and so on. Fine. So, we have done the first two things, that is writing A as LU and A as BC, where was the A equal to BC was the rank factorization. Here I would like you to see that why is rank of B equal to rank of C is equal to R. I have not given you an argument, but the simple argument is that P inverse is invertible. So, if you have any matrix A, let me not write A here, say any P which is invertible, fine, then any collection of rows of P will have full rank, all right. Similarly, any collection of columns will give me full rank, all right. That is important. So, here look at this, the rank of B1 will be R and rank of B2 will be m minus R, because the rank of this whole matrix, the rank of B1, B2 is m, all right. So, it means that every row has a pivot, every column has a pivot. Is that okay? Because the rank is m, so every row, every column has a pivot. Similarly, Q inverse has a full inverse, so it is invertible. Therefore, all the rows have pivots, so there are pivots, therefore you get it. Is that okay? So, that is for now. We will look at some ideas of this in the next class. Thank you.